2 degree of freedom, undamped, free vibration. Like we saw when we were first starting looking at 1 degree of freedom systems and finding their total solutions, we're going to start with the simplest case in 2 degrees of freedom, when we have free or autonomous systems with no dissipation, no damping. So if we're already done with the modeling step, we have our equation in motion. In this identify step, we're going to see that these types of systems are all going to look like this. We're going to have our right-hand side is 0 because it's an unforced system and it's the 0 vector. There's no forcing acting on either of our 2 degrees of freedom. We have no x dot term, so there's no, the C matrix is 0. There's no damping, no dissipation in our system. So we just have this M matrix and this K matrix on the left-hand side. Right, so very similar format to what we saw for 1 degree of freedom, but now we have M matrix, K matrix, not just an M scalar value and a K scalar value. So when we have these types of systems, we're going to be able to form a general solution that actually will look fairly familiar and look kind of like what we saw for 1 degree of freedom. So our closed form solution is going to have the form of this C1 chi1 cosine plus a C2 chi2 cosine. So notice all the terms we're going to be having here. We have this Omega1 and Omega2, so these cosine terms are going to be oscillating at 2 different frequencies, Omega1 and Omega2. And the Omega1 and the Omega2 are the 2 natural frequencies in our system. So once we go beyond 1 degree of freedom, there is no the natural frequency. We have as many natural frequencies as we have degrees of freedom in our system. Now we have these 2 cosine terms, unlike the 1 cosine term that we saw for 1 degree of freedom systems. So they each oscillate at one of our 2 natural frequencies, and they each are going to have this phase delay, a phi1 and a phi2. And those are going to be found, like we saw with the 1 degree of freedom systems, phi1 and phi2 are found using our initial conditions. Now, going to this coefficient in front of the cosines, we have a C1 times a chi1 and a C2 times a chi2. The chi1 and chi2 are the mode shapes of our system, and these are going to come from the M and the K matrices, as we're going to see the Omega1, Omega2 also come from the M and the K. So the mode shapes and the natural frequencies come from the system parameters, the mass matrix, and the stiffness matrix. The C1 and the C2, like with 1 degree of freedom, are also going to come from the initial conditions. So 4 unknowns we're going to be able to find from our 4 initial conditions because we have 2 degrees of freedom. So each one is going to have an initial position and an initial velocity, giving us 4 initial conditions, so 4 algebraic equations to find C1, C2, phi1, and phi2. The natural frequencies are going to come from the eigenvalues using M and K, the mass and the stiffness matrices. I'm not going to go through all of the math that's involved here, but it is going to be coming from the homogeneous solution to this equation. Now in this case, it's free vibration, so the homogeneous solution is the total solution, but this method is also going to be true when we get into forced systems, that still it comes from the homogeneous solution to our problem. But more or less, we can relate this back to when we found the characteristic equation for the 1 degree of freedom system. A similar type of process is going to come into play here, where we're going to get this omega squared coming from the x double dot and then no omega coming from the x when we were finding the characteristic equation. But skipping a couple of math steps here, we're going to be able to find the omega value, the omega squared value, which we sometimes call lambda. And lambda is going to be the eigenvalues of M inverse K. And actually, this does look a lot like what we saw for 1 degree of freedom systems. And if we think there, for a 1 degree of freedom system, the natural frequency is the square root of K over M. If we look at what we're doing here, we also have, but in matrix form, M inverse is analogous to 1 over M, and then we have K. So the stuff here is kind of like a K over M, just in matrix form. And when we have a 1 degree of freedom system, since m is scalar and k is scalar, if we take the eigenvalue of a scalar, it just returns back exactly that scalar value. So this method actually does work in 1 degree of freedom, but it doesn't really make sense to be doing this because we don't have matrices to be working with. But it would work for a 1 degree of freedom system. So if we take the eigenvalues of this m inverse k, that is going to give us lambda. Now in 1 degree of freedom systems, there's a single eigenvalue. So that is how we're getting, it just would come out to k over m, and that is our natural frequency squared. Well, that's exactly what we saw in 1 degree of freedom. However, now in 2 degrees of freedom, we're going to have as many eigenvalues as the dimension or the size of this matrix m inverse k. Well, when m is 2 by 2 and k is 2 by 2, m inverse k is also 2 by 2, which means we're going to have 2 eigenvalues, 2 values of lambda. If we take the square root of each of them, that is going to be the 2 natural frequencies that we have in our system. And these are going to come out as real values when we're dealing with these undamped systems here. So lambdas will be real, purely real, if we do this correctly. What I recommend doing then is putting them in ascending numerical order from lowest to highest when we are going to be identifying the Omega1 and the Omega2. So I like to have Omega1 always be smaller than Omega2. And when we go to multi-degree of freedom systems, Omega1 will always be the smallest, then Omega2, Omega3, however many we have. Now this is not necessarily a rule, but it's going to be easier to keep track of the eigenvalues, thus the natural frequencies this way, and as we'll see in a second, the associated mode shape, the chi1 and chi2. So what's going to be important as we go forward is that chi1 is associated with Omega1, chi2, the second mode shape, is associated with the second natural frequency, that the order does matter, or the pairing does matter here. So I will assign Omega1 to be the smaller, Omega2 to be the larger of the 2 natural frequencies from this step. So again, to kind of recap here, the natural frequencies of the system are the square roots of the eigenvalues of m inverse times k. That is how for 2 degree of freedom systems and higher, we're going to be able to find these natural frequencies. All right, so with a process for finding the natural frequencies, now we can go on and start to look at these mode shapes. The mode shapes are just the eigenvectors of this system, this same m inverse k system. Again, I'm not going to go through all of the math here as the background, but more of the process. One thing to note when we find mode shapes, and you saw this when you took your ordinary differential equations class, or your matrices class, or both, that the mode shape is not unique. That is to say, the eigenvector is not unique. Because the eigenvector and any scalar multiple of it is also the eigenvector of the system. Now, typically, we're not going to be calculating the eigenvectors by hand, where the typical way for a 2 by 2 system, we would set the first eigenvector equal to some unknown constant, and then 1 is the second entry, and then we would go through this equation and find the A1 value. And then we would do the same thing to find chi2, the second eigenvector. We would do something similar. We're not going to do that usually if we're using MATLAB or Mathematica or some other tool. We're going to let it find the eigenvectors for us. So the actual eigenvector itself, we can scale up or down, and it's still an eigenvector of our system. However, the ratio of the values is going to be unique in our eigenvector. So A1 divided by 1, that ratio is the same as if I multiplied this whole thing by 10, I would have 10A1 over 10. Well, the ratio is still preserved. So that's the unique part about the eigenvectors. What we want to be just careful with or aware of is if you use, let's say, MATLAB to find the eigenvectors of our system, we might get different answers than if you use Mathematica, because MATLAB by default is going to have each eigenvector have a magnitude of 1. Whereas if you use Mathematica, it by default is going to try to make the bottom value equal to 1, and thus the magnitude of our eigenvector is probably not 1. So we might get different answers, but they are going to be scalar multiples of each other. And again, that is exerting that the eigenvectors are not unique. There can all be scalar multiples of each other, and we can still have the right value. And we'll see how that comes into play on the next slide, how we can have different values for chi1 and chi2, and both of them be correct. So we're going to find the eigenvectors of this system. Typically, we're going to do this using software. So if we're in like MATLAB, we can do the eigensystem of M inverse K, and in one fell swoop find our eigenvectors chi and our eigenvalues lambda. And then just remember that the natural frequencies are the square roots of the eigenvalues. And if we're going to be reordering our eigenvalues or our natural frequencies from smallest to largest, we have to remember to also have the associated eigenvector then go in the same order. When we're using software, it does not necessarily automatically come out in ascending order of eigenvalues, so we might need to rearrange the order of this chi. Also note, if we use MATLAB, chi is going to come out as a square matrix, where each column of it is one of our eigenvectors. If we use something like Mathematica, the way that the eigenvectors come out might look different than how it comes out in MATLAB. So we just want to be familiar in the software that we're using. How do eigenvectors come out? Do they come out as columns or rows or as a whole matrix like it does here? So to quickly recap this, the mode shapes, the chi values, are going to be the eigenvectors of M inverse times K. So we have our eigenvalues, which tell us our natural frequencies. We have our eigenvectors, which tell us our mode shapes. Now we can start to put together that solution, that general solution that we had earlier. Right, so we have that general form that x of t is going to be this cosine term plus a cosine term operating each at one of the two natural frequencies. Again, I recommend putting omega1 the smaller, omega2 the larger one, and then the associated chi with that value of omega. So lower natural frequency associated with that lower, with that eigenvector, and then the higher natural frequency associated with its eigenvector. If we take x of t and do a time differentiation on it, then we get x dot of t. So again, if we look here, this is using chain rule, and we see what we get out in front of as our coefficients in front of now a sine term and another sine term, or a negative sine term and then a negative sine term. So we want these x of t and this x dot of t expressions because we still need to figure out C1, phi1, C2, and phi2. Again, we know omega1, omega2, chi1, chi2 by now, coming from the eigensystem of M inverse times K. Now we have to apply our 4 initial conditions to find our 4 remaining unknowns. So remember, we're going to be provided with initial conditions. So for the first degree of freedom, what is its initial position, its initial velocity? And for the second degree of freedom, what is its initial position and its initial velocity? Those are the 4 equations we get out of this. Going back to these equations quickly, take note these are both vector equations because chi1 and chi2 are going to be vectors. So they're going to have here 2 rows to them because we're going to have bold x of t, or vector x of t, is really x1 of t and x2 of t below it. So this is one vector equation, and then this is a second vector equation. So that's where these 4 scalar equations are going to come from. If we want to know what's happening to x1, here I'm just using a superscript. So this is the first degree of freedom is x1, or the first degree of freedom's velocity, x dot super 1. And then this 2 is just indicating that it's the second degree of freedom. This is not meant to be a first power or second power, nor is it here. This is just the first degree of freedom, initial condition. Second degree of freedom, and initial conditions is what the notation is trying to say. So, solving simultaneously these 4 scalar equations, we'll be able to provide a C1, C2, phi1, and phi2. And the way that we're going to be solving these simultaneously does get a little bit tricky. We're going to use, for this course, the similar numerical technique to what we used in Unit 1 when we were looking for two unknowns and two equations. We're going to use that fminsearch kind of hack together to find our the four variables that satisfy the four equations, because something like f0 is not going to work because here we have four unknowns and four equations, and f0 will only work on one equation and one unknown. And solving these by hand can be really tricky. So we'll get to actually solving these as we go through the following examples and actually apply our initial conditions. So once we have solved these, we can figure out the C1 and C2, the phi1 and the phi2, and then we have our complete closed form solutions for the position, and if we need it, the velocity as well.